Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, I'm very pleased to start out the fourth day of this workshop. And this morning our first talk will be from Junfeng Fan of Katholieke Universiteit Leuven on ECC and small devices.
Thank you. So good morning, everyone. I didn't expect so many people after the banquet and hungover. So I would like to thank the organizers to invite me. Normally mathematicians or engineers don't sit in one room and discuss what to do. Yeah. Normally it's algorithm is ready and someone come to us and say, please implement it. Yeah. Just do it. It's just a multiplier. Why are you hesitating? Just please do it. So I would like to take this opportunity to give you a short report on what we are doing and what are the challenges, what are the problems we encounter, and I mean maybe you are doing it in a inefficient way or probably even in the wrong way, or you come up with a better idea. So that would be great. So the topic of the presentation is ECC on small devices. So the first question you want to ask is, what is a small device? So what are we talking about? So is iPhone a small device? Well, you can hold it in the hand, but iPhone has a processor, 32-bit processor running at 600 megahertz. It has up to 32 gigabytes storage. It's not a small device. Yeah. So this is a small device. So maybe you cannot read it. It says TPM 1.2. That's the Trusted Platform Module. It's produced by Infineon. If your computer was produced after the year 2006, you probably have it in your computer, but it's not switched on. Normally it's shipped with, it's deactivated. The basic thing it does is after you push the power on button, it checks the BIOS, the bootloader, to make sure that the configuration of your computer is the same as the previous one. And they normally use hash function to do it. And then to check the hash value of your configuration is not changed. And then you go to the next step, to load the middleware and so on. So by doing this, you can achieve certain degree of trust. So it's called Trusted Platform Module. Microsoft is one of the partner of the member of this Trust Computing group. The second one I'm going to show you is a magic card that you put it somewhere in a machine and then you get goods or service, and it gives you the illusion that you actually didn't pay for it. So this thing here is a smart card. So it basically includes some information of your account and some signature and certification and so on. So currently it's using RSA. And third example I want to show you is a RFID tag. It's proposed to replace the barcode. So it's a very small device. So why do we want ECC on this thing? So currently, this one has a RSA coprocessor, and this also has a RSA accelerator. But it is suggested that we should use ECC. But RSA currently works fine in these devices. So ECC is a candidate, but when are we going to switch to ECC? It's not clear yet. But this device, it's very small. So you see this thing here is a tiny device. If you want to put crypto there, ECC is no longer alternative. It's probably the only choice you can use. So I will describe a little bit more why do we want our ECC on this kind of device. So an RFID tag has two parts. Basically, you have a small chip here that basically stores a bit stream. It's identification. It's basically the ID of the tag, and surrounded are the wires, which is basically antenna. So how does it work? So this thing has no battery, so it has no power supply itself. So when you want to read the data from this small chip, you establish the electromagnetic field, and the antenna will harvest the energy and store it on a capacitor, and then do the computation and also the communication. So it's a very small device. It's very cheap. This thing is so small that it's a challenge to attach it to the antenna. So it's now widely used, for example, for supply chain management, for inventory tracking, and so on. So if you go to a pharmacy, you probably have it here on the bottom of the bottle. So by doing this, the people working in the pharmacy don't mix up the drugs, don't give you the wrong drugs. And in the future, it probably gets more intelligent. Like it tells you when this was produced and how many pills you should take every day, or it actually even reminds you that you should take your pills now, and so on. So the second application is for pets identification. It's actually mandatory in some countries that if you have a dog or cat, you actually have to put the RFID tag inside the body. It's implanted. So if it's lost, you can easily find it. If someone finds it, he can easily identify, who is the owner of this little lovely thing. A third application of this is for anti-counterfeiting. So this is a ticket for the Shanghai Expo this year. It actually has an RFID tag inside. So when you go to the expo, you show your ticket, they read it with a reader, and they make sure that this one is authentic. It's not a fake one. So you say that for this kind of applications, RFID tag has to be unclonable, and otherwise there's no meaning for doing this. And the fourth application I'm showing here is mobile payment. So you can actually put a bank card inside the RFID and attach it to your cell phone. So you can use it for public transportation, or you can buy something in a vending machine. So you no longer need to carry your bank cards. You carry a phone, and everyone has a phone all the time. So that's going to be a very nice and application in large scale. So, but there's a little problem. You heard this anti-RFID protest from time to time. And the problem is privacy. So, if someone is standing in front of you and you don't know him, it's a stranger. He's basically anonymous to you. You have no information about him. But if he's carrying some RFID tags and you take a reader, you see, you probably can read the ID, the EID card that he's carrying, his name, his birthday, and the country where he's from. He probably doesn't want to reveal this information to you. Or, he's driving a Porsche. In some country or some place, this may cause him trouble. Some criminals will say, this guy is rich, let's rob him or something. He doesn't probably also want to reveal this information. Or maybe he's carrying some pills, that indicates that he has some disease, and this is not good when he's going to a job interview. So we want to use this technology, but we want to keep the privacy. An RFID tag system is usually, it's one reader or many readers with many tags. So what makes a good RFID tag? It works. That's the first requirement. It's cheap. That's, if you talk to anyone who works in this industry, it has to be cheap. Otherwise, nobody's going to use it. It's secure. So this is a little bit, ambiguous. So what does secure mean in this context? They have some sort of definition for this. Secure means that an only authenticated tag a legitimate tag can authenticate itself to the reader through a matching conversation. So it means that if you change the conversation or if you fake a tag, you should not be able to authenticate yourself to the reader. It's untraceable. It means that the adversary should not be able to identify a tag from the previous sessions. And it's scalable. That means you have millions of tags. It should be easy to add or to remove tags from the system. And it's reasonably fast. You don't want to stand in front of the vending machine for 1 minute to finish the reading, right? So let's look at the requirements. Yeah, it's cheap. That means it has small area because every gate, every single gate in the circuit costs you some amount of money. So it has to be small. It has to be secure, and that's where the crypto jumps in, right? We need cryptography to ensure these properties. It has to be untraceable and it has to be scalable. If you look at this topology, it looks like very nice for public cryptography implementation applications. So there are studies on this, and they show that if you want to ensure this property, you actually really need public cryptography. And it's fast, so it has to be lightweight. So the complexity should be low. If we put all of them together, that somehow, maybe we can use ECC for it. Right. Okay, let's take a protocol as an example. So this one is proposed by Schnorr in the year 1989. It's identification protocol. So it is suggested to be used in a RFID system. So the tag has secret information. It's a private key X, and the reader has its public key stored on the reader. So what the tag does every time it generates a random number, and it computes. It does 1 point multiplication and sends this R back, and the reader generates one random number and sends it to the tag, and tag performs this operation and sends this V back. So then the reader checks if this equation holds. If it holds, that means the tag really knows this secret X. So it works, but there's a problem. If you see that all this information are transferring in the air, so any adversary can eavesdrop it. So if you have this 3, and you can easily derive the public key of the tag. So every time you just try to compute this big X, and if it's the same, that's the same tag. So it can be traced. So new protocols to be proposed. There's another one proposed by Vaudenay in the year 1907. So the idea is like this. So I'm not going to go through the protocol again, but the basic idea is that the tag also does one encryption, but the encryption is a random encryption. So it's a probabilistic encryption. It's not deterministic. And he claims that if the encryption algorithm, so the public key crypto system, is indistinguishable, to a chosen cipher, a plain text attack, this scheme is secure. Is a narrow, strong, private. So strong and narrow are like the way you identify an attacker. So strong means that an adversary can open the tag, can read the ID, the key out, and close the tag and put it back to the system. So that's a really strong adversary. And narrow means the adversary does not know that reader accepts it or not. So he doesn't know the decision of the reader. So if an adversary falls into this category, he is a narrow, strong adversary. So this scheme is narrow, strong, private, means that even the adversary is this strong, he still cannot trace the tag. If the encryption system has this property. So this sounds nice. We can implement this. But you need to choose public key cryptography to do this job, and should be efficient and should be securely implemented. So, okay, let's make an ECC for this. An ECC chip, when you make an ECC processor for this kind of applications, you always have some constraints. For example, you should have small area, as I mentioned before. You should use small arithmetic logic unit. You should reduce the storage to make it small, and you should take energy into account when you make the chip. And the performance is another constraint, so you should ensure a reasonably fast computation. And also, there are sophisticated physical attacks on the chip, so we should make the chip secure enough to prevent these attacks. So, I mean, I will describe a little bit of the design flow of hardware. I mean, since most of the audience here are mathematicians. So, when we design the hardware, we start from the design capture. Like, we want to make an ECC processor. Okay, that's the design capture. You can write it in C or C++ or Magma or whatever. You describe the thing that you want to implement. And then you transfer it to a lower level language. Normally, it's called HDL, which is hardware description language. In many cases, it's a Verilog of HDL. And then you do synthesis. It's like when you write C code, you do a compile, generates assembly code for you. So up to here, it's only a structural. So there's no physical information in the implementation. So normally you write the HDL, you do synthesis, and you do some simulation. If it doesn't work, you go back. You go several loops until you're satisfied here, and then you give this implementation to the backend designers. So they do floor planning, they do placement, routing. Eventually, they give you a circuit, a layout. So that's how it is designed. So, okay, this is the layout of a circuit. So you say, you couldn't say much thing here, basically. There are many logic cells connected, and this thing is sent normally to Taiwan or Singapore or somewhere produced, and you get the chip back. So you say that when this thing gets large, it's really impossible to do it by hand. So that's why we have. So from here, all these things are done by tools, by software. So you don't really see what in assembly code. You can still trace it to see where is this thing stored, a pointer and so on. But for hardware, it's somehow difficult in the end to somehow correspond something here to the thing you have here. Okay, so some terminology. Gate equivalent, that's the unit we use to count the area in hardware design. So gate equivalent is actually to measure how many equivalent NAND gates you used in your design. A NAND gate is something like this. So it's very simple. Y is the inverse of A times B. So that's the smallest logic gates in the library you have. So we use it as a unit to measure the area. And also with this gate, actually, you can construct any functions. So this is the memory cell in hardware. So you use to store information. Roughly, it's the area of this thing is 6 gates. So the size of this thing is 6 times this, roughly. It depends on the library. So why is this interesting? Because now you say that it's very important to reduce the storage. Let's compare RSA and ECC. Let's say ECC 163. And we say that we can reduce the storage by 6 times 163 bits. So that makes 97.8 bits to be stored in the hardware. And if you take RSA, that has the equivalent security, you need 2 elements in this group. Then you need to store 2048 bits. That's significantly larger than ECC. So in applications like this is a huge difference. If you can use ECC, you probably don't want to use RSA. And okay, so ECC looks better in this scenario than RSA. So how about hash function? You can also use kit hash function to do authentication and so on. Let's take a look at these SHA-3 candidates. So there are still 14 left in the second round. If you look at how many bits they have to store in the memory, it's actually not much less than ECC. Of course, this is we take 256-bit digest, so it's the security level of this thing is a bit higher than this. But some of them are using much more bits, store much more bits than ECC. Some are less. So hash function is actually not so small if you compare the size of ECC. Okay, so hopefully by now I convinced you that ECC is a good candidate for these applications. So we want to make an ECC processor. We have to make some decisions. What field we should use? We can use binary fields, we can use prime fields. How many bits do you want to secure your RFID tag? And what coordinate systems? How do you represent your elements? Polynomial or normal or others? And what kind of architecture and what kind of physical security properties you want? So the first thing, we look at the difference between binary fields and prime fields. Yeah, so this is the adder in a Galois field. So you basically only need to do one XOR operation. And this is one bit addition in the prime field. So you see this thing is significantly larger than this one. And multiplier is basically built with a bunch of adders. So it's not so difficult to say we should use binary fields. And the second one is security. Yeah, so we have a lot of choices. So ECC 131 bits. If we implement this, I guess Tanya will say that's a silly idea tomorrow, right? Because this thing is practically solvable, right? Okay, let's move to ECC 191, and then your boss will say that's a silly idea. Because if ECC 1K63 can do the job, why do you use 191? I mean, that's a waste of money. So yeah, we use this one. If you look at the papers so far, for RFID tags, ECC, most of them are used. I think all of them are used this. That's the reasonable choice. So next question is what coordinate system you should use. If you take a look at this, I didn't list all of them here, but just to give an idea. So you see that for affine coordinates, for each point, you need two elements to represent. And the thing is that you need inversion in each k bit. And that we don't like. It's very expensive. For projective coordinates, you don't have inversion. You probably need one in the end, but you need three elements. And we know that this storing 163 bits is very expensive. So it's also not so interesting. And low pitch dahab, you actually can use only x coordinates. So it's very nice. You only need one element for each point. But you also need, in a affine version, you also need inversion. And low pitch dahab, projective version, you need two, but you only need one inversion if you use Montgomery ladder. For binary Edwards curves, you have something similar. It's the W coordinates in affine version and projective version. So we use low pitch dahab projective coordinates. So less inversion, less storage. That's the choice. So let's look at this low pitch dahab coordinate system. This is the group law for addition and for doubling. So you have 2 points. Each one has two coordinates. If you count it, you need 7 registers. 4 of them are used to store these 2 points. 1 is used to store the base point, and you need 2 temporary registers. And for doubling, something similar, but you need 3 registers. And this is only possible when you use Montgomery parent ladder. So how about further reduce it? There's one trick to do this. So basically, you say that we make the z coordinates of the 2 points the same. So after the point addition, point doubling, you somehow cross multiply the x coordinates, z coordinates, and you unify the z coordinates for both points. So by doing this, you only need 1 z coordinates, so you can reduce from 7 to 6. And it seems that you need 3 more multiplications, but actually it's not true, because you have made the z coordinates the same. So for the next iteration, you can save some operations. So the penalty is that you move from 6 multiplications plus 6 squarings to 7 multiplications, 4 squarings, for using when you use this common z coordinates. And to further reduce the hardware cost, you can also simplify the regist file architecture. I guess this is probably not so interesting here. So basically, you for a normal regist file, you can access every register from outside. And this one, you can only access A, and if you want to put something in C, you first put it in A and you shift it. So you somehow simplify the interconnection, and which also reduces the area. So that's the trick we played to reduce the hardware, the area. So the next question is power. So remember that this thing has no battery. So it harvested the energy from the field. So you need to reduce the power consumption of this thing such that the energy you get can, let you finish your computation and do the communication. And also, the distance between the reader and tag also depends heavily on the power consumption you use. You see that the closer the tag is to the reader, the higher the energy density is. So you can have more power. So if you want a larger distance, this thing has to be using even lower power consumptions. So just to illustrate how the power is consumed in a circuit, this is the inverter. So when the input goes from high to low, the output goes from low to high. And the other way around is the same. So when the input goes low to high, the output goes from high to low. So that's like the basic element in the circuit. That's what we learned the first class for digital circuit design. And the power. So when you say that when the input goes from high to low, the output goes from low to high, and that's when you charge the capacitors here. And when it goes from low to high, you discharge it. So it goes from like this. So when you charge or discharge the capacitor, that's where the power is consumed. So if you count how much power is consumed, it depends on basically four factors. The first one, alpha, that's the switch activity. So you say that the more you switch, the more power you consume. The second one is C, which is the output capacitance. It's basically the value of this thing. So the larger this is, you need more power to charge it. The third one is the voltage, so the supply voltage. Obviously, the higher it is, you consume more power. It's also it has a larger impact than others because you have a square here. And the last one is frequency. It's also obvious, The higher frequency is, you consume more power than this. So just a side note that why that Intel is moving from moving to multi-core system instead of keep increasing the clock frequency of their processors. And one of the reasons is that the power density is just too high. So if you go from to 10 gigahertz or so on, keep increasing the frequency, then it consumes too much power that the metal wire inside the circuit will melt. So it doesn't work in that way. So what you do, okay, let's just keep the frequency 1 gigahertz, 2 gigahertz, and we make multi-cores. And we just copy it, paste, 4 core, 8 cores. And we know it's difficult to program it, but that's not the problem of Intel, right? So that's basically okay. Another reason is also for verification. So when the circuit gets too large, it's almost impossible to fully verify the circuit. So instead, you just make a circuit that you can fully verify, but you copy paste, and then you paralyze your applications. So we somehow do the same thing here, and the idea is basically the same. If you look at the multiplier, this is a very simple multiplication algorithm. So you want to multiply two elements represented in polynomial basis. You scan one bit by bit, and you accumulate, and you do a reduction. So this is the circuit that you use to perform one iteration of this. So you say that you have A of x here, it comes, and it's multiplied by 1 bit of B of x. So that's the multiplier. So basically, if BI is 1, AX goes through. If BI is 0, all of them are 0. And then you add them. So this thing is gates. You add them to say of x. Say of x is shifted one to the left, and then you do one reduction. So that's the circuit. So if you have this circuit, you have to use m clock cycles to finish the loop. Now, in order to make it a bit faster, we can actually use multiple bit serial multipliers, and that's what we call them, bit serial multipliers. Concatenate them together, and you make a digit serial multiplier. So now you can finish, let's say, if you have d bit serial multipliers, then every cycle you finish d iterations. So you only need m divided by d cycles to finish it. So why is this interesting? Now we want to make an ECC processor that can, we set a target. We want to finish one multiplication within 250 milliseconds. Okay, so that if your protocol has two scalar multiplications, it's done in a half second. You can change this, but basically that's what we said for the protocol we want to use. So now if you increase the number of digit size, the digit size, so let's say the number of bit serial multipliers in your multiplier, and you see a drop in the, you can drop your clock frequency. So here we have 5 lines, and there are area, cycles, frequency, power, and energy. So the first thing you look is the frequency, because now you have, from here to here you have larger multiplier. You can actually drop your the frequency to achieve the same delay. So you see that from 1 to 2 to 3, you have a dramatic drop of the frequency, and which leads to a dramatic drop of power consumptions. But if you keep increasing the digit size, you see that the energy consumption almost stays. You don't gain much here anymore. So that's where you stop. Because if you keep increasing the digit size, you actually also add cost to the hardware. You make it larger. So this is a trade-off. At some moment, you say, okay, if we keep increasing, we gain less, but it costs more. So that's what we're going to use. So we use digit size 4 in this application. Okay, that's the end of the power consumption. So we also need to deal with physical attacks. There are two types of physical attacks. The first one is side channel analysis. The second one is fault analysis. So, like 15 years ago, we believed the circuit, the cryptographic circuit we make is a black box. You only see the input and output. You don't see what's inside. And this is actually not true. This is a classic way to bypass you don't really need the key, but you can use some other information to test that your guess is correct or not. Like here is sound, and in side channel analysis you use power or electromagnetic radiation or timing, or temperature. You use this to gain information from the chip. And another one is fault analysis. I will give an example for both. So this is a typical setup, simplified setup for power analysis. So you have an ECC processor here, and you want to measure the current that's flowing through the ECC processor. So what you do, you insert a resistor here, and you measure the voltage drop here. That's basically is equivalent to the current that's going through it. And you measure it with the oscilloscope, and you see it on the screen. And we call this thing a power trace. So a simple example is this one. This is a classical left to right binary method for point multiplication. You scan the scalar bit by bit. And when it's 0, you do a doubling. When it's 1, you do doubling and addition. So easy to understand. And if you look at the power trace, it actually tells you the key stream. So because when the key bit is 1, it takes more time because it first has doubling and then addition. So you see this part is longer than this one. So this part indicates this bit is 1. And this is 0, another 1, another 1, another 0. So basically, if you only need one power trace to read out the completed key. So it's very simple, but it's very powerful. So we have to prevent this attack. So we have a very nice algorithm, a Montgomery powering ladder. So you do always do point addition and point doubling, no matter the k is 0 or 1. So it's balanced somehow. You don't see that you don't see this thing in the power trace anymore. But there's one thing we have to be careful. So this balance is actually in the algorithm level. So it's balanced, mathematically balanced. But that means it's balanced up to here. But what we really want is that it's balanced here. So when you implement it, you can actually make something that screw up the balance. So in the end, you still see the difference in the power trace, and that basically can be used to compromise the security. A more sophisticated attack is differential power analysis. So the basic idea is that you have a real chip, and that has a key stored somewhere there, and you have a power model. So that's something used to model the power consumption of this thing. So what you do is you run many executions, many point multiplications with different base point, and you measure the power, and that's what you get here. And then you make a k guess. You guess that, okay, let's say the first 2 bits of this k is 0, 1. Now we only guess the first 2 bits. So you have only 4 possibilities. You can really guess it. And then you give the same inputs, and you get the output here. But since you have a power model, you can actually give a hypothetical power consumption of the computation of the 2 k bits. That's something here. Now, you look at this, let's assume that this part is the end of the second second k bit. Then you check this vector and this thing. If your guess is correct, then they are highly correlated. So you can use some statistics to compute the correlation of this thing and this vector. And you can try different guesses, 4 of them. One of them will have larger correlation than others, and that's the correct k guess. And now you have the first 2 k bits, and then you guess another 2 k bits. You keep moving. So that's how you recover the whole key. So it's very powerful. So in order to prevent this, you have to somehow randomize the data that you are computing here, or somehow completely make it constant. The power consumption is just 1 line. You don't see a difference, but that's very difficult. So there are many techniques to do this. And now we move to fault analysis. So you can actually open the chip, and so this is a typical setup, and this is a laser gun. You open the chip, you shoot it with a laser, and that can somehow flip some bits of the data you stored in the memory, or change the multiplication, or so on. So it's possible. So assume that we have a nice implementation with a key here, and it's secure against the power analysis. So what it does is that it takes the input P and computes P, K times P, gives you the output. Now, if we look at the curve, this is the curve actually we wanted to use, and we give the input P, which is on the curve. But if the adversary can, change some bits of y coordinates to make it another P prime, and this actually P prime is defined is a point on another curve, right? So the only difference is you can find another curve that differs from this one only in A6. And this A6 is not used in the point addition or point doubling. So you can actually choose a y coordinates here such that this point is on this curve, and this curve E prime is a weak curve. So you can use the output, and the output is also a valid scalar multiplication result on this curve. So you can use this output and this input P prime to solve the ECDOP on this curve to get the key. So okay, that says we should verify the base point before I actually do the point multiplication. So you check if the curve parameters are good, are not affected, and you check if the point P is on the curve or not before you actually start the point multiplication. But, okay, can the adversary actually injected fault after the validation step. So you do the validation, but right before you are going to do the scalar multiplication, the adversary can inject the fault. So how are you going to deal with this problem? The question is that possible? Yeah? Is that possible? How likely that you hit a weak curve by inject a fault here? So there's a tag proposed 2 years ago at the FDTC. It makes use of twist curves. So consider a curve to find our prime field, and as we mentioned before, we don't want to use y coordinates, so we only use x coordinates. Then this curve has a quadratic twist, and the twist curve can be a weak curve. So now we are using this x of p to represent the point. If the adversary managed to insert some random fault on this x point coordinate, actually he has a very high probability to end up with a point on its twist. The probability is almost 1/2. So you can actually hit a weak curve, and the weak curve is its twist. And I think this was not really, I guess it's not really taken into account when NIST recommended curves, because some of the NIST curves also have this property. So, okay, so let's just do another point validation. So before we output the point, the result, we check it again if it's on the original curve or not. But you can do the same thing. You can inject another fault right before you are going to validate again. Right? That's possible because you have a high probability to move it back from its twist to the original curve. So how are we going to solve this problem? So, okay, this table is probably too small to read from the back, but that's okay. So basically, we put all the known attacks and the known countermeasures in one table. And we want to see that how they interact with each other. For example, this is simple power analysis, timing analysis, and we have a couple of countermeasures. Like you use indistinguishable point addition, point doubling. You can use double and always algorithm. So basically, you always do doubling and addition, no matter the KBD is 0 or 1. If it's 0, you do a dummy operation. So just to make it look the same in the power trace. But you see, this algorithm is not good for fault analysis because you inject the fault in the addition operation. If the result is correct, that means that operation is dummy. That means that KBD is 0. So this countermeasure is actually helping another attack. And if you look at the whole table, you see quite some of them. So the H here means that this countermeasure is helping another attack. And sorry, I should explain that the hook here means that this countermeasure is effective to this attack. Cross means that this countermeasure can be attacked by this attack. And question mark means we don't know or it's not published. And dash means that it's not related really. And star means it's really dependent on how do you implement it. So what I want to see is that if you look at this table, that we only actually understand a small part of the known attacks and countermeasures. And how to choose the countermeasures to make a secure implementation is it's still not quite clear. Okay, now if we come back and look at the protocols. So if an adversary wants to attack a implementation of this Schnorr's protocol, and where he's going to attack? Well, he can attack the random number generator. You can make it extremely low temperature. You spray some liquid nitrogen ions, and so the random number generator gives you a BIOS, the random number. So you don't have 163-bit entropy, but you only have 80 or something, and then that significantly lower your security. Or you can attack the scalar multiplication part, for example, like what we described before above. You can also attack the integer multiplication and addition. You only you get R1 or you get X. They are the same. You only if you get one of them, the security of the system is compromised. So it would be nice if when you design a protocol, we take this into account. like how many attacking points are there, and we try to minimize the attacking points. You know, like make some of these operations less sensitive. The attackers can have it, but it doesn't help you. I mean, that would make our life much easier. Okay, so these slides I want to show that what would be nice if we have it. It's basically like I have a dream. Yeah. So how about we want to reduce the storage, and we want to represent the point with only x or x coordinates plus 1 bit, because anyway you have x and the y coordinates is 1 bit information, and this probably already exists. But we don't want inversions there. You know, we want x coordinates only, and we don't want inversion. Probably with no multiplications neither, only addition and squaring. And there's no weak twists. So you cannot make use of weak twists. And a random bit, you know, a random float, 1 bit, 2 bit, n bits, floats on the parameters, you know, A1 to A6 is not likely to hit a weak curve, such that you cannot, you know, insert force to the parameters. And the protocol has minimized attacking points. There's only one, or there's no attacking points, for example. It would be great. And we want lightweight countermeasures. Yeah? So every countermeasure you use, you add extra hardware, you need more time, you need more energy. So we really don't want countermeasures. Okay, so these slides just to show some implementation results. So we have implemented the ECC, 163-bit ECC, 163-bit binary Edwards curve, hyperellipse curve defined over 83 bits, Galois field, and true. Just to say the performance. So there's a small difference here. Actually, you should not take into. We cannot say, okay, this one is a bit higher than, you know, binary Edwards curve. It's a bit better, a bit larger than ECC, so that ECC is smaller than binary Edwards curve. That's not true. It's a small, you know, change in the configuration of the tool will give you this difference. So what we can say is that binary Edwards curve, elliptic curve, and hyperellipse curve, they actually can be almost the same area. And the power consumption, they are also more or less the same. The N2 is significantly lower if you only use the encryption. But you should also take into account that this parameter no longer gives you 80-bit security. I think it's much less. So if you want to 80-bit security, you have to use a significantly larger N and Q. So that will look different here. N2 encryption and decryption together, the area is not much smaller than ECC. But the message is that ECC can be made small. It can use only 13K gates, and the power consumption is less than 15 microwatts, and that's probably already feasible to put it on a passive RFID tag. So this is the layout of our chip, and it has been sent to Taiwan, and we expect it coming back next month. So maybe after 2 months, I can give you more data on the really measured power and performance. So yeah, this part is a full custom part. So it's really designed by hand, just to try to balance the branch in the Montgomery powering ladder, and the rest is some controller and you know, to support different protocols.
Is this multi-core?
No, it's only one core. Yeah. So yeah, that's it. Yeah. Thank you.
Are there any questions? If I didn't drive, the tag does not identify the reader in any way. So don't you have a total breach of privacy because Osama bin Laden can bring his reader and read the tag?
Yeah, that's true. So if you really want strong privacy, you need mutual authentication. So, but that makes this very difficult because you have to store the public key or, you know, certificate of the reader, and that adds much more storage and and also limits your applications. But that's a good point.
What were your design choices for the chip that you now have?
The design choice?
Yeah. I mean, you presented different curves, different something, so...
Yeah. So this chip, we actually used the elliptic curve, 163-bit elliptic curve, Montgomery Powering ladder, sorry.
So the one from the standards?
Yes, it's a couplet curve.
If that chip were laid out by hand, how big would it be, and what technology, of course? Because RFID is mass market, so you don't have...
How big you mean, sorry?
How big would the chip be if it were designed for a mass market with hand layout?
You mean the size of the layout?
The size of the chip, yes.
So I think this was like, I don't really remember the actual size. No, I can look it up because I didn't do the post layout part. We did the higher part, the front end part. Yeah. But it's definitely much larger than the RFID chip you have now, I think. Yeah.
Any other questions? Rich.
You were showing the virtues of XOR versus full carry adder. It seemed to me you cheated a little bit because those XOR gates are really 2 or 3 hands.
Yeah, true.
So the relative comparison was less.
That's true. Maybe I just...
It was near the beginning.
Yeah, but full adder also has like 2 XOR gates and couple of addition. Yeah, that's right.
Any more questions?